Hello, we are Thomas, Nikhil, Yash, and Saurav, and our project is automatic speech recognition with synthetic speech. Here's a little challenge for you. One of these audios is real and the other is synthetic. Can you spot which one is which?
The rainbow is a division of white light into many beautiful colors.
She was fond of all boys' plays and greatly preferred cricket.
Impressive, right? Much of the current strides in NLP research, specifically in automatic speech recognition, focus on the English language. However, the English language accounts for only 16.5% of all language across the world's population. This leaves quite a disparity in representation as much of the remaining speakers haven't had access to SOTA ASR in their language. This reality can be primarily traced back to the large amount of accessible English speech corpuses available for training these complex ASR systems. All of these are heavily documented and tested on collections of speech and become used in training benchmarks across the field of NLP. Even among these English datasets, most of the data is for American accents, ignoring other dialects. This issue gave rise to the inspiration for this project. We are aiming to test the hypothesis of solely synthetic speech being capable of training a speech recognizer that is comparable to a model trained using actual human speech. If proven to be true, this eliminates extra costs required in obtaining and curating large real speech datasets suitable for training top-of-the-line speech recognizers and allowing much more of the world's population to have access to these ASR systems. This is the overarching approach to test this hypothesis. In brief, the goal is to utilize the popular Libri speech dataset and the transcripts within the corpus to generate equivalent synthetic speech using the speech synthesizer VITS. Then both the original and synthetic speech are then being used to train separate listen, attend, and spell ASR models. The output of each of them are then evaluated against metrics and compared. Now let's dive into each of these components.
Looking into the dataset that we used the LibreSpeech dataset for this project. It is a famous corpus of Red English speech. The entire dataset consists of around 1,000 hours of speech at a sampling rate of 16,000 Hz. The dataset itself requires two prior pre-processing steps for it to be successfully ran on through our LLS models. For the input of the original WAV files are first converted into MFCC spectrograms with 27 feature dimensions using the librosa Python package, which is specifically used for music and audio analysis. As for the transcripts themselves, due to their format, only little further pre-processing was required for training to commence. The original format consisted of a single string of characters representing the spoken sequence. The characters were then converted to a list of strings with the addition of the start and the end of sequence tokens.
Moving on to the speech synthesizer being used for this project. The speech synthesizer that we used in this project is the variational inference with adversarial learning for end-to-end text-to-speech, or WITS for short. The model utilizes a variational autoencoder to allow for more efficient learning. It also utilizes a proposed stochastic duration predictor, which is used to capture the variations found in speech by altering things such as pitch, rhythm, and duration. This model works significantly better than the previous works, as it creates multi-speaker audio, which is important to make the ASR more robust and generalized. As for the speech recognizer being used, we use LAS, also known as Listen, Attend, and Spell, as the automatic speech recognizer. This is an encoder-decoder system. The encoder, which is a listener, is at the bottom and takes in MFCCs and encodes them into a latent representation. The decoder, which is the speller, is at the top and is tasked with decoding the latent representation into the character distribution at each step. The attend portion of the model is an attention mechanism used to extract the key components found in the output of the encoder.
Now let's look at the metrics that we use to evaluate the performance of the model. For the results, we calculate the Levenshtein distance, which is a number that tells you how different two strings are based on the number of edits that need to be made to the string. We obtained a distance of 12.16 after 80 epochs with the natural data compared to 42.2 with synthetic data. A part of the difference can be attributed to the difference in the size of the data, that is 65 hours of synthetic versus 100 hours of natural speech. To put the numbers into words, the sentence on the left is the ground truth from the Libri speech dataset, and the sentence on the right is the output from a recognizer. In summary, the use of synthetic speech has shown great potential in the field of speech recognition. For future work, we plan to experiment with other languages and dialects, providing an opportunity to develop speech recognition models for a more diverse range of languages and dialects where there's a lack of natural transcripted speech. Thank you.